Okay, I think we can begin. Thanks for coming. I will send out an email, but you may be thrilled to know that Scott Potter is going to come and talk to our class on Monday.
Nice.
He's the guy who was involved in the negotiations about buying the wind for OSU from Blue Creek, and he's going to come and he's going to talk about that and maybe some other things, so I'm looking forward to that. Here he's pretty good. But I'll send out an email and remind everybody. So you don't want to miss class. He wants to have a discussion. I'm going to invite the distance people to come too. We'll see if they do. All right, so today's topic starts with geothermal power. So this is the last renewable energy source, well, maybe not renewable, but sustainable, because the Earth is pretty big, that we've got left to play with. So let's hope for good things out of this. So the good news is that the Earth is hot down in the middle. The bad news is that it's hard to get down to the middle of the Earth, and you could cool parts of the Earth if you're trying to take heat from the crust, for example. If you take it too quickly, it doesn't get replenished by thermal distribution from the core quickly. So there's a limit to how quickly you can remove the heat. And I just realized I need to press this button so the distance guys can see the screen. Maybe if I press preset and then this button. Yeah, all right. So, geothermal power, there's basically two sources. One is, the core is molten, and then there's the mantle, and there's heat flow from the molten core up through the mantle. It amounts to about, and notice the number here, 10 milliwatts per square meter. So all those other energy sources we were talking in terms of how many watts per square meter, this is milliwatts per square meter. And this is surprising. There's also heat generated in the crust itself by radioactive decay of elements that are just naturally occurring there. Amazingly, that's 4 times greater, 40 milliwatts. It's still not a huge thing, but it's non-trivial. 40 milliwatts per square meter from radioactive decay. So the total flux of heat from inside the Earth out is 50 milliwatts per square meter. So if you figure that out for Ohio, and you figure how many people, and how 50 milliwatts per square meter, and so forth, it worked out to 11 kilowatt hours per day per person. Not insignificant, if we can get it. That is the max potential, but it turns out there's no easy way to extract all that heat. If you dig down to where it's really hot, you miss out on the radiation energy. That only happens in the crust. So, if you figure a third efficiency, this is the book's number, and maybe 5% of the land used, oh, darn. Maybe we could get 0.2 kilowatt hours per day per person in Ohio. Not as big as I was hoping. So here's a quiz for you. Which is the lowest quality energy? Electrical, mechanical, chemical, or thermal? Oh, we have a shy class. How many people think it's electrical? No one's buying that. How many people think it's mechanical? Nobody thinks that. How many people think it's chemical? How many people think the lowest quality energy is thermal? Right. Which is what the Earth is offering us through geothermal. So, it's energy. It's not the greatest, but it has uses like heating. So, how does it work? Well, if you happen to live in Mammoth Springs, Yellowstone, there's hot springs there, and you can just put a tube and pump hot water into your basement and run it up through your house and heat your house. Unfortunately, in Ohio, it would be a pretty long way to pump that. I think they would run out by the time they got North Dakota or so. So we don't have hot springs in Ohio that I know of. Second way is a heat pump. So the idea here is that you drill these wells. So here's some vertical wells here. The water is pumped out of your house. Let's say you're trying to cool. So you take hot water from, because it's summer, and you pump it out here, and you pump it down into the ground, and as it goes down here, it interacts with the cold earth, because the earth is 50 to 60 degrees maybe, and if it's 80 degrees outside, it's cooler down there. So as your water gets pumped through these tubes here, it cools down, and it comes back as cool water, which you can then run through your house and try to cool your house down. So the water goes in there, and you're trying to either warm up the water, or in this case, cool it down. But in winter, I just reverse it, right? I still take the water out of my house and I pump it down, but now Maybe it's 40 degrees in the house and the water's cold and I'm trying to heat it up to 60 or 50 or 60. It's not great, but it's something. And pump it back in and use it for heating. So I can only warm up or cool off the water gently because there's not a big temperature change. And then you pump it back into your house to gently heat or cool your house. This method is being used on the 4-H building on campus over next to the Schottenstein. That's just Schottenstein. And it's this style where they have these vertical wells. So the building has a big parking lot out behind it. And before they built the building, they drilled all, before they built the parking lot, they drilled all these vertical wells, and you go into the basement of that building. They give tours sometimes. You should go if you get a chance. And they'll show you all the pumps and stuff in the basement. They've got monitors that show the temperatures of the waters going various places. They're also starting to do this for these dorms on South Campus, that big mess that they're drilling all those holes now. They ran into a bunch of problems because evidently there's a lot of water and mud and stuff underneath there, so when they're drilling these wells, they kept collapsing. I'm hearing, I don't know, I don't have that verified. But they had a lot of problems, unexpected technical problems, but they're still putting them in. And they are expected to supply, now notice this, about 1/3 of the heating and cooling used by these dorms. So it's not a huge energy source, but it's something. A third way would be if you were conveniently living near geologically active places like, oh, I don't know, California or Yellowstone or someplace. Then you can drill down to where the heat is hot enough to boil water. You take that boiled water, you use it to make steam, you drive generators, that's known as a dry steam plant, or you can bring up the water under pressure so it's superheated. And when you release the pressure, it turns into steam suddenly, boom, and it drives a turbine, that's a flash steam plant. Or you can just bring up the hot water and use a heat exchanger to transfer the heat to some liquid. So a heat exchanger would be if you had two pipes near each other and one was, or maybe one pipe inside another, and one is carrying hot water and the other one's carrying cold water. The energy, thermal energy will flow between them and exchange heat from one to the other. Geothermal flash steam plant. Gosh, that looks like a link. Oh yes, it's going to work.
Welcome to one of Cal Energy's geothermal power plants. Unlike other power plants that rely on coal or other fossil fuels to create electricity for homes and businesses, thermal power plants use superheated fluids from the Earth's geothermal resources to generate electricity. The natural heat of the Earth creates geothermal resources. This heat comes from molten rock called magma, located at the Earth's core, deep below the geothermal resource. Over thousands of years, rainwater seeps through cracks in the Earth's surface and collects in underground reservoirs. The magma heats the water until it becomes a superheated fluid. To reach the superheated fluid, wells are drilled 5,000 to 10,000 feet below the surface of the Earth. These wells, called production wells, bring the superheated fluid to the Earth's surface, where it can be used to generate electricity for homes and businesses. This geothermal power plant uses crystallizer reactor clarifier technology, a process that turns the geothermal superheated fluid into steam while removing solids from it. The steam is used to drive a turbine and generate electricity. All remaining geothermal fluids are injected back into the reservoir for reuse. Under its own pressure, superheated fluid from the geothermal resource flows naturally to the surface through production wells. As the liquid flows toward the surface, the pressure decreases, causing a small portion of the fluid still within the well to separate or flash into steam. At the surface, the superheated fluid and steam mixture flows through surface pipelines and into a wellhead separator. Inside the separator, the pressure of the superheated fluid is reduced. This causes a large amount of the superheated fluid to rapidly vaporize and flash into high-pressure steam. The geothermal fluid that is not flashed into steam in the wellhead separator flows to a second vessel called a standard pressure crystallizer, where an additional amount of standard pressure steam is produced. The flash process continues in the low-pressure crystallizer. The remaining fluid is again flashed, this time at a lower pressure to produce low-pressure steam. All of the low pressure, standard pressure, and high pressure steam is delivered to a turbine. The fluid that is not flashed into steam flows into the reactor clarifier system and is then returned to the geothermal reservoir through injection wells. Turbines are the primary piece of equipment used to transform geothermal energy into mechanical energy. Pressurized steam created from the geothermal superheated fluid flows through pipelines to large steam turbines. The force and energy in the steam is used to spin the turbine blades. The turbines turn a shaft directly connected to an electrical generator. An electrical charge is created when magnets rotate within the generator. Large copper bars carry the electrical charge to a step-up transformer outside the plant. Within the transformer, the voltage is increased before the power is sent to the power lines that carry it to homes and businesses. Geothermal energy is a sustainable resource because with proper management, a geothermal resource can remain a renewable source of energy. Water trapped deep within the earth will naturally replace the superheated fluid that is drawn from the geothermal resource through surface wells. However, it is possible to deplete the geothermal resource by removing fluid faster than it can be naturally replaced. To help prevent this, the steam used in the geothermal power plant passes through a condenser that turns it back into fluid. At this stage, it's possible to recover minerals from the geothermal fluid before it's injected back into the earth. This condensed fluid, along with the fluid that did not flash to steam, is injected back into the underground reservoir. Magma naturally reheats the fluid so it can be used again.
I gotta figure out how to get out of here. One of these things. Oh, this. And this. What? Go away. Okay, so when they say if it's carefully managed, what do they mean? Is it if it's carefully managed, they can continue to bring heat out of this? The key is you can't bring out the heat too fast. You can't deplete that water supply, that superheated water supply, or if you're just taking heat out of bedrock, which we haven't talked about yet, you can't remove the heat too fast or it doesn't get replenished. So there's a maximum rate at which you can get energy out of these things. According to this map here, Ohio is this color that says 40 to 60 milliwatts per square meter. If you live in these areas like Yellowstone, that would be good. What's here? Is that Colorado? One of these is Colorado. I get them mixed up. I think that one's Colorado. I forget. I don't know what's there. Okay, so here's a plot of geothermal as finite resource. I'm going to show you several plots. Here's one. Here's the same data plotted another way. Here's the same data plotted another way. And here's the same data plotted another way. So if I ask you, is the data linear? What do you think? Which graph did you look at to decide that it was?
Bottom left, bottom right.
Bottom left, bottom right. So if the question is the data linear, what I'm hearing is that it's easier to determine that from these. So this is just a little side trip about presenting data, technical data, effectively. D. Whatever. So if someone asked you, what's the data, is the data linear, which graph did you look at? You said C or D. What is the temperature at 8 kilometers? So this is depth in the crust horizontally and temperature vertically. If you want to know what's the data at 8 kilometers deep, which graph would you look at, probably?
High, top right.
Top right. So, and what do you get, 200? That's what I think, it's about 200. So here's some guidelines. No 3D ever. The only time you ever want to use 3D in a plot is when you actually have three-dimensional data. This is, there's a term for it, chart junk. It's superfluous. It doesn't help convey the message. It just looks fancy and doesn't do any good. Label all the axes. Use lines if the graph is a continuous quantity. So here, the data is continuous. Here, it's shown as if it were discrete, but there's actually a value for 8.5. So if you have continuous data, you want to draw a line graph. If you have discrete data, you might put points here, or you might use a histogram or whatever that line chart, bar chart is. No chart junk, make graph as clean as possible. Here's an example. Who needs this, right? There's only one line on this curve, so I don't need this to tell me that it's temperature, because I know it's temperature versus depth, so I would get rid of that. It's just an example of chart junk. A lot of times when you use Excel to plot things, it puts all that stuff there. It's hard to get rid of. So just be thinking about that, especially for making presentations. Avoid heavy grid lines. I don't know. I don't see heavy grid lines there. Actually, I will add, if you're making a presentation, like on PowerPoint, there's no real point in putting all these tick marks here. The reason you put tick marks on a graph is because if someone has a piece of paper, they can take a ruler, pretend I'm using a piece of paper, and they can read values off the graph, and they can actually write on the paper. But on a chart, no one's going to do that. So if there's a particular point you want someone to notice, like 8 kilometers, get rid of the tick marks and just put the point there and say 200 degrees. Or whatever that unit is. Current crust temperature in degrees Celsius. Ooh. Well, too late. All right, so back to our regular scheduled program. So geothermal is a finite resource. It'll be there for a long time. We can extract energy at a finite rate. And effectively, what you're doing is mining heat. So, geothermal mining. How many kilowatt hours per day, assuming Colorado, let's pick Colorado because they had some geothermal stuff there, extracts 100 degrees C from a cubic kilometer of crust. So this is up above the mantle at, say, 10-kilometer depth once every year. And notice you could do that every year, so you could keep doing that, but there's a limit to how fast you can take it per year. So here's 1 cubic kilometer per 5 megapeople per year, 100 degrees C, converting joules per centimeter. This is a specific heat, I think, et cetera, et cetera. And whoa, works out to 23 kilowatt hours per day per person if you live in Colorado. So Colorado has geothermal energy. For us, the number turned out to be, well, she didn't assume 5% of Ohio, or of Colorado that I see. I think she's assuming, well, she says 1 cubic kilometer of crust. So I don't know how much of, I don't know if we can compare that number to ours because we did it by saying 5% of Ohio we were extracting. But Colorado has geothermal, so they may not need to drill as much. So it may be cheaper for them to make geothermal energy because they have bigger temperature differences there. The U.S. currently makes about 1.1% of its electricity via geo at the surface. That's hot springs and pumping hot water, and maybe as much again for heating. So geothermal wells like we have on campus. So I tried to find some information about Ohio. I found that the Ohio caverns, which are about 100 feet deep, they're consistently 55 degrees Fahrenheit, so wear a sweater when you go tour them. The salt mine in northern Ohio is 2,000 feet deep. It's actually hotter, 80 degrees Fahrenheit. And if you go deeper yet, like oil and gas wells, maybe 8,000 feet, it's 160 degrees Fahrenheit. Notice it's not boiling yet. Heat pumps, shallow heat pumps are widely used. So that would be like what we have out in the parking lot of the 4-H building. So can we add it to the stack? I wanted to add this to the stack for Ohio. I was trying to figure out how to find numbers. So I thought, well, I know that heating and cooling depends on the energy difference between a hot and a cold place. OSU dorms are not currently air conditioned, at least the ones that they're putting the heat pumps in for. And the ground temperature is 55, so maybe the maximum temperature difference would be about 40 degrees Fahrenheit. And then I got stuck, so I tried another approach. I thought, well, I read in the Lantern that these pumps are going to use 34% less energy than the natural gas system. But I'm thinking natural gas, you don't use that for cooling, you only use that for heating. You use electricity for cooling. So that must mean the heat only. And they said it was going to save $200,000 a year. So $200,000 a year. So I looked up how much natural gas would that be. It'd be about 400,000 cubic CCF. Something about cubic feet. Now I don't remember what that stands for. And I've worked that out to how many megawatt hours, but I found out how much natural gas costs. But then I couldn't find a figure for how many students were in those dorms, so I still don't have a number. I'm just trying to give you some ways that I was approaching the problem. All right, so here's where we are now, if you live in the UK. So we are out of sources. We've used every sustainable energy source that we can think of. Except for nuclear is not on here, and we're going to talk about nuclear in a later class. Some people want to add it to the stack, and some people don't. We're going to treat it separately, and I'll let you decide. We're out of sources, and we already have more consumption than sources, but we're not out of uses yet. Here's another example of something we spend energy on, which is defense. Here is a plot for the U.S. military. And this pink thing, so here's some chart junk. So I tried to put some letters on here, or maybe they put some letters on here. Coal, that's this. The military doesn't use that much coal. They use some natural gas. This is electricity. Distillate and... What's that? I don't know. I don't know what distillate is either. But look, jet fuel. Whoa, I know that's made out of petroleum. And motor gasoline is not that much. This is used for those convoys in Afghanistan. So, we can, from this, get a feel for how much energy the military uses. So I did it for, I got some 2008 numbers that are not on this graph. And the answer was 890 trillion British thermal units, which works out to 260 billion kilowatt hours per year. So if you divide that by the population of the United States, it's 2.3 kilowatt hours per day per person. And then I added in, so it didn't include nuclear, I added in McKay's estimate for our expenditure in nuclear defense for the last 50 years. That was another 1.7 kilowatt hours per day. So nuclear is included in this military number. And with that, our number came out to 4 kilowatt hours per day per person, which surprised me because it's the same as the UK. I would have thought we've got this massive, massive military. Of course, we have more people. So 4 kilowatt hours per day per person. So here's a summary for the UK. Geothermal is not that significant. The services, military is a small but significant chunk of energy use. All right, so now we're pretty much done with the stack. So let's go back and review some stuff here. What does a person in the UK or the USA use the most energy per day for on the average? We have heating, transportation, food production, or defense and services. Heating, transportation, we got bites on transportation. Food production, defense, heating. Here is the graph again. I don't think this is right because here's the car and the jets and then transporting stuff up there. I think it's transportation. I think this is wrong. Yeah, transportation. So cars, planes, transportation of food, transportation of other goods, totals about 85 kilowatt hours per day per person for the UK, and who knows what it is for us, probably something like that. So how do we find these numbers? And this is how engineers think about it. We take the equation for whatever we're doing, and we say if I want to increase or decrease this quantity, let's say I want to decrease the energy per day, then I've got a fraction here, to decrease this, I should make the numerator smaller, or if I divide by a big number, I can make the result smaller. So I want to decrease numerators and increase denominators. I could have also changed the amount of time, but that's cheating. Can't do that here because I want to compare it to other numbers. So I want to decrease numerators and increase denominators. All right, here's a quiz. Which renewable method can contribute the most energy per person in the UK? Solar, thermal and PV, wind on land and sea, biomass, or tide and waves? I don't know if this is going to circle the answer. Oh, look, here's the chart. What do you guys think? Solar? It's not going to be biomass. It's not going to be tide and waves.
Solar.
Solar. This says wind. Here is 13, 10 is 23, 50 is 73. That's solar. Wind is 16 and 32. What's that? 48? What was the first number?
Bottom 120, it's 60.
Oh yeah, 60? So wind.
It's still less than 73.
Oh yeah, you're right. So who made this chart? Clearly whoever it was on drugs. So here is for UK. So in Ohio, notice I have revised the Ohio stack because we found some more recent data that showed our water usage was much greater. So the data we used to compute our original numbers said UK used 50 units, I forgot what the units were, and the US used 70, and then we found some other data that said we used like 2 or 3 times as much. So I used that more recent data, and that changed the heating and cooling number considerably here. So I just want you to know that I monkeyed with the data. Some of this is based on calculations for Ohio, and some of them I could not find numbers for Ohio. So I used McKay's numbers for transporting stuff, for food and farming. Cars and planes. Actually, the cars ones is comparable for both countries. Planes, we don't have any idea. Stuff, gadgets, and lights, I said were comparable. I couldn't figure out how to get data for that. Notice that this does not include energy we use to pump water around from the reservoir to your house, pumping gas to your gas station. Well, I guess we deliver it to your gas station. And oil, or we pump natural gas to your house so you can light the stove. And then there's the Alaska pipeline, so those things aren't included there. And does not include the energy costs of drilling or refining the fuels. But neither do McKay's numbers. So it's not looking too good. Which renewable method can contribute the most per person, energy per person in Ohio? Solar, wind, biomass, or hydro? What do you think? Solar. Yeah. So why are we putting in wind? It's got to be cheaper. Got to be. What? Biomass? 22 kilowatt hours per day? Let me go back. I don't even see biomass on here. I think that's got to be a typo. So, how do our estimates look so far? Here's the UK estimates. The UK, he's estimating a use of 195 kilowatt hours per day per person. So let's remember that number because we're going to look at this stuff in a bunch of different ways. And possibly could generate 180 kilowatt hours per day per person. USA, greater than 250 kilowatts. We're not exactly sure. I think my last number was 270. But we have more potential for production at 250 kilowatt hours per day. The green stack makes a lot of assumptions. Okay, so you believe that those are not realistic estimates. Do you believe those are optimistic? Okay. The red stack does not include various efficiencies, and I'm not sure what's meant by this because we included the efficiency of extracting, for example, with solar, we include the efficiency in there. I think it must mean doesn't include the efficiency of refining the oil and that kind of stuff. All right, so here's a plot with no vertical grid line. So I lost some chart, not junk. Quadrillion BTUs, and this is years from 1950 to 2000. And believe it or not, we do export a tiny amount of energy, not too much. Here's production, and here's consumption. And here's imports. So production plus imports will give us our consumption, minus exports. And one thing to notice is that our energy consumption is increasing. No surprise there. I'm trying to, so I was going to use the SAR consumption. I figured that out. 229 times 10 to the 12th kilowatt hours per year works out to 257 kilowatt hours per day per person. So this was a sanity check. Those numbers that we got by estimating all those different things, probably not too far off. That was in maybe 2000. What's it likely to be in 2013? So I just drew a line. This is a guess. I did not do an experimental fit for you mathematicians. And I took a line to 213. I extended this to scale. And I'm thinking maybe 300 kilowatt hours per day per person might be our current assumption. Our current consumption based on extrapolating this graph, not based on the estimates we did for the various consumptions in our stack. Here's consumption by sector. So let's see who's using up our energy. Commercial is increasing. Residential use is increasing. Transportation is increasing. Industrial use, surprisingly, is more or less level. I think that's strange. Interesting. This data comes from Minnesota for Sustainable.org. I don't know why, but there you have it. Energy use in the U.S. has become more efficient. So if you consider the amount of energy consumed to produce $1 worth of gross domestic product, fell from 20.6 kilobtu's to 10.6 kilobtu's, so that's a 49% improvement between 1949 and 2000. So for every dollar's worth of stuff that we produce, it takes less energy than it used to. However, we're producing more stuff. Our population is up 89%. Our energy consumption's up 208%. Our per capita, you and me, use is up 63%. If it hadn't been for these improvements in efficiency, we'd be much worse off than we already are. Here's another way to slice and dice. Residential and commercial energy consumption. Losses include energy lost during generation, transmission, and distribution. So this one does take into account, oh, here, this is the losses. Whoa, I don't like the look of that. So it looks like we're using less coal for residential and commercial because we're using the coal to make the electricity. So this would be people burning coal in their actual homes or in their plants. Here's electricity, petroleum, gone down because we're using petroleum primarily for transportation. Natural gas, we increased that, it's leveling off. Don't know what's going to happen here. People are saying, oh, now natural gas is the way to go. I know, let's dig holes in the ground and put poisonous fluids down there. And then here's the losses. Ooh. So, why are the losses increasing so much? It isn't because things are getting less efficiency, it's because we're using more energy. And we can't avoid the losses. Here's industrial uses. Industry burning wood, interesting. I wonder, I don't know, but I wonder if this is energy use or if this includes people who make things out of wood. Just saying, pencil factory. Electricity is increasing. Coal, decreasing. Losses, same problem. Industry, petroleum, kind of spiked there and it's leveled off a little bit. Natural gas is all over the place. I believe that there was, from reading The Quest, which has turned out to be very good, there was an increased interest in natural gas right here where people thought it was going to be cheaper, then the prices shot up, and now people are looking at it again. What will transportation use look like? Here is petroleum and total transportation. So again, reinforcing petroleum is primarily used for transportation. We're not burning it to create electricity much. Here's vehicles. Now this is a weird graph. This one's been normalized. So they created some kind of index and they set it to equal 100 in 1973. So all this thing does is shows you trends. Okay? So fuel consumption has gone down from gallons per vehicle from 1973 numbers. We have more fuel-efficient vehicles. People are driving smaller cars. Mileage per vehicle is improving. That's good. That's why this is going down. Fuel rate, miles per gallon. Whoa. This says we're driving more miles. This is per vehicle, and this is miles per gallon. So we're driving more. Oil embargo, energy crisis happened there. That's why they picked that time. I remember the oil embargo. You guys are too young. But I was just first learning to drive back in 19 Every time you wanted to buy gas, you had to go to a gas station, wait in line for an hour. And you really planned when you're going to the gas station. You looked to see who had gas. It was pretty bad. It's a good time to learn to drive because it keeps you thinking about energy all the time. Here's consumption by sector in 2008. This is for the, oh, there's no citation on here. I believe it's for the U.S. Transportation is 28%, industrial is 31%, residential 22%, and commercial 19%. This is huge. This is huge. This tells us why people are thinking, buy your food locally, buy food that was produced locally. But food, of course, only a tiny part of it. What I'd like to do is buy my car that was built in Ohio and my computer that was built in Ohio. All right, according to this data, and I'll show you the data again, what is the approximate home power consumption in kilowatt hours per day per person in the U.S. in 2008? Oh, here's the data. 20 quad BTUs residential consumption per year. There's no sense, you don't have a calculator, and there's no way to guess. We'll just cut right to the chase. Turns out it's about 100 kilowatt hours per day. So again, home power consumption, 100 kilowatt hours per day per person. This is approximate, it's actually closer to 66. This is an approximation. So here's a calculation. 40 quad BTUs is that many zeros. I divided by 365 days per year, divided by 300 million people. We have a little bit more than that. I got this many BTU. I took that per day per person, converted it to kilowatt hours, 100 kilowatt hours per day per person. That's just residential. And we said our total usage for the U.S. was maybe 250, 270, 300 kilowatt hours per day per person. So about a third of that is going to residential. It didn't say resident. Yeah, it did say residential. There's a little bit of a disconnect there. Driving home the point that it's hard to get good numbers. 1,000. Oh. Yeah, as if you didn't know. All right, so according to this data, what is the approximate total power consumption in kilowatt hours per day in the U.S. in 2008? About 100 quads BTU. Total power consumption kilowatt hours today. I'm looking to see, oh, so I believe what we're doing is we're adding up the commercial, the residential, transportation, and industrial, add up those four numbers. 270. So this sort of corroborates our estimate. We said we knew it was going to be more than 250 when we were building up our stack. Just another way to try to get at that, see if our numbers make sense. Compared to McKay, U.S. actual, according to that data, was 270. McKay estimate for the UK was 195. UK actual consumption was 220 milliton oil equivalent for entire country, 115. And then here's his caveats. Doesn't include the energy in imports, which McKay included. Does not include the energy in food, which McKay included. Does not include conversion losses between one type of energy and another, or energy in transmissions. But, of course, neither does the U.S. data. So, according to that, if we compare this number to this number, we're far worse than the UK. This number came from this chart here, but the 250 or greater that we had before came from some wild guesses on our stack. Well, they weren't too wild, but they might be partially wild, slightly domesticated. Efficiency of energy delivery, primary and total consumption by sector 2008. Primary consumption, I believe, means Oh, it says on the next slide. I happen to remember this. Energy in the form that is first accounted for in statistical balance before any transformation to secondary or tertiary forms of energy. For example, coal can be converted to synthetic gas, which can be converted to electricity. In this example, coal is primary energy, synthetic gas is secondary energy, and electricity is tertiary energy. So, here's efficiencies. In quadrillion BTUs, residential 6.8 out of 21.6 total use. Commercial, industrial, transportation, electric power. If you consider electric power to be your primary source of energy. Although, what if you're using, see here, what if you're using electric power to create heat? Then the heat would be the secondary form. They don't show that, do they? That's going backwards. Primary energy consumption in the end-use sectors, plus electricity, retail, sales, and electrical system energy losses. Electric power generation. Again, no surprise here, especially if you watch Don Caston's talk and reinforcing all the same things. To generate power, we don't burn oil much. Here's renewable energy. I think that this is going to start to go up, but it has a long way to go before we get to that. Nuclear energy, leveled off. Is nuclear energy going to come back? You should read the quest, it's very interesting. How do the major energy sources balance? Residential, commercial, industrial, transportation. So residential, here's renewable energy at residences. It's pretty small. Oil, electricity, natural gas, for my stove, electrical losses, whoa. Commercial, we don't see renewable energy on this one at all. Coal is down, electrical losses, electricity. Industrial, here's some renewable energy. I wonder if some of that isn't hydro. Not so much coal, electricity, electrical losses, gas and petroleum. Transportation, here's natural gas, here's petroleum, we're done. No electric vehicles shown there because this only goes up to 2010, looks like. How is the supply distributed? So these are the sources of energy. This is a neat chart. Petroleum says where it goes. 71% of petroleum goes directly into transportation, or 94% of transportation comes from petroleum. Of the petroleum that we have, 22% of it goes to industrial, or industry uses 40% petroleum. Natural gas, tiny bit goes to transportation. We saw the last slide, and these are about evenly split to those guys over there. Coal, industrial is 8%, residential less than 1%, 92% into electric power. Again, no surprise. Renewable energy, we're excited about this. 14% goes to transportation. Transportation, 4% of it comes from renewable sources. Maybe electric vehicles are counted here. I'm looking for a date. I don't have a date on this. Let's see, 28% goes to industrial. Industrial, 11% of its energy comes from renewable sources. Renewable, 8% goes to residential, people putting thermal energy on their roof, I'm guessing. And 50% goes to electric power. So of the renewable energy we make, half of it goes to generating electricity. But if your electricity, and you're being generated, 48% comes from coal, 10% comes from renewable, 21% comes from nuclear, it's not negligible, 19% from natural gas, and only 1% from, excuse me, petroleum. I think that this is a good place to stop. The reason I say that is that the lecture I asked you to watch on Monday when I was sick is much longer than an hour. So I'm cutting this class short so you guys don't get messed up. And we'll start with looking at affluence and GDP against energy use next time. Are there any questions? Don't forget Scott Potter Monday. Be there, be square. Have you all picked up your quest? Okay, good. It's very interesting. I'm going to assign a few chapters. I haven't decided which ones because they're all so good. All right. Run and play. What?
Next Monday?
Yeah, this coming Monday. Scott Potter's going to come and talk. I'll send out an email so the distance guys will know too. Oh, which reminds me, I better turn off the recording.